All right, let's dive in. We're going to talk about two words you use every single day: work and energy. But what if I told you that in science, these words mean something completely different, something really specific and kind of cool? Yeah, you might be surprised. So let's get right into it.
So, let me ask you something. Think about the last time you were just drained. Maybe you were studying for a huge exam for hours, or you tried with all your might to push a car that was stuck. You felt wiped out, right? You definitely say you did a ton of work. Well, get this. Physics might just look at you and say, nope, you did zero work. How is that even possible?
Okay, so look at this. It really lays out the confusion, right? On one side, you've got what we call work, cramming for a test, trying to budge a massive boulder, or even just holding a super heavy box still, all totally exhausting. But then on the other side, you've got what science actually calls work, lifting a book, pulling a wagon, walking up some stairs. So what's the big secret? What's the one thing that separates just feeling tired from doing real scientific work?
All right, to figure this whole puzzle out, we have to get into the nitty-gritty of the scientific definition. And here's the spoiler. It has nothing to do with how much you sweat or how tired you feel. It's all about meeting two, and only two, absolutely crucial conditions.
And here they are, the two roles of work club. First, you gotta have a force. Simple, right? A push or a pull on something. But second, and this is the absolute deal breaker, the object has to move. It needs to actually go somewhere. If you've got one without the other, no work is done. So that wall you were pushing earlier, yeah, you were using a ton of force, but since the wall didn't go anywhere, scientifically speaking, the work you did was a big fat zero. Crazy, right?
And of course, there's a super simple formula for this. It's just work equals force times displacement. W equals Fs. That's it. It's a really clear connection. The harder you push, or the farther you make something go, the more work you've officially done. It's really that straightforward.
But wait, it gets even cooler. There's a little twist. Imagine you lift a book off a table. You're applying a force upwards, and the book moves upwards. Easy. That's what we call positive work. But hang on, gravity is still there, right? It's pulling the book down the whole time. Since the book is moving in the opposite direction of gravity's pull, gravity is actually doing negative work. So yeah, direction matters a lot. Okay, so now we've nailed down what work is. But the next big question is, what does work actually do? Well, its whole job is to transfer energy. Think of it like this. Work is the action, and energy is the stuff that gets transferred. Let's dig into that idea a bit more.
I love this analogy. If energy is like the money of the universe, then work is the act of spending it. It's the transaction. You can't just create money out of thin air, and you can't destroy it. You can only move it around, transfer it from one account to another. That's exactly what work does for energy.
So here's the bottom line. The official definition of energy is simply the capacity to do work. If something has energy, it means it has the ability to exert a force and make something else move. And because work and energy are just two sides of the same coin, it makes sense that they're measured using the exact same unit.
And that unit is the joule. It's named after this guy, James Prescott Joule, a British physicist from back in the 1800s. He was the one who did all these brilliant experiments that connected the dots between heat, electricity, and mechanical work. He showed it was all related. So every single time you lift your coffee cup or flip a light switch, you're literally transferring energy, measured in joules.
Now, energy shows up in a whole bunch of different forms, chemical, thermal, you name it. But for what we're talking about today in mechanics, we're really going to focus on two big ones, and they are constantly in a dance, trading places with each other. Those two forms are potential energy and kinetic energy. And the simplest way to remember them is this. Potential energy is stored energy. It's energy that's just waiting, ready to go. Kinetic energy, on the other hand, is the energy of motion. It's energy that's happening right now. So one is all about potential, the other is all about action.
A stretched bow and arrow is like the perfect example of potential energy. Think about it. When you pull back that bowstring, you're doing work on the bow, right? That energy you just used doesn't just vanish. It gets loaded into the bow, stored up in the tension of the wood and the string. That is pure potential energy, just sitting there waiting for you to let go. And then you let go. In that instant, all of that stored up potential energy transforms into kinetic energy, the energy of motion. And that energy gets dumped right into the arrow, sending it flying through the air. That's the conversion, happening in a split second, from waiting to doing. So basically, if it's moving, it has kinetic energy. It's that simple.
And the faster it's going or the heavier it is, the more kinetic energy it's packing. A speeding car on the highway, a coconut dropping from a tree, even the water rushing from a dam to spin a turbine. They're all just different flavors of kinetic energy in action. So this back and forth, this constant trade between potential and kinetic energy, it's not just happening randomly. The whole show is being run by one of the most important, most fundamental, and absolutely unbreakable laws in the entire universe.
And that is the law of conservation of energy. This is a big one. It basically says energy cannot be created and it cannot be destroyed. Ever. The total amount of energy in the universe is fixed. All you can do is change its form, convert it from potential to kinetic like with the bow and arrow, but the grand total, it always stays the same.
Let's make this super clear with a falling ball. Picture this. You're standing on top of a tall building, holding a ball over the edge. Right now, in this moment, it's perfectly still. So its kinetic energy, its motion energy, is zero. But because of its height, it's absolutely maxed out on potential energy. It's just loaded and ready.
Okay, now you open your hand. As the ball starts to fall, it loses height, right? So its potential energy starts to drop. But at the same time, it's picking up speed, so its kinetic energy is shooting up. See how they trade? The potential energy goes down, the kinetic energy goes up. And if you could pause it exactly halfway down, you'd find its energy is split perfectly, 50-50 between potential and kinetic.
Now what about that split second right before it smacks into the pavement? Well, at that point, it has basically no height left, so its potential energy is pretty much zero. But it's also moving at its absolute top speed, which means its kinetic energy is at its peak. Every last drop of that potential energy it started with has been converted into the energy of motion. The transformation is complete, and the total energy from start to finish, exactly the same.
Okay, let's recap. We've got work, which is how we transfer energy. We've got the two main types of that energy, potential and kinetic. But there's one last piece of the puzzle we need to talk about, a word we use constantly, power. And power, well, power is all about speed.
Power is just the rate of doing work, or you could say it's how fast you transfer energy. It has nothing to do with how much work you do, only how quickly you get it done. So if you and I both lift the same heavy box, but you do it in half the time I take, you've just used twice as much power. Simple as that.
This example with the two girls climbing a rope just makes it perfectly clear. Take a look. Girl A and Girl B, they both do the exact same amount of work. They both lift their weight the same distance. But look at the time it takes them. Girl A zips up that rope in just 20 seconds. Girl B takes 50 seconds. So even though the work is identical, because Girl A did it so much faster, her power output is way higher. It just goes to show, being strong and being powerful, not quite the same thing in physics.
So there you have it. The next time you're moving things around or running up the stairs, you can think about it like a physicist. It's not just about the effort. It's about the force, the distance, the energy you're transferring, and how fast you're doing it. Which brings me to a final question for you. Thinking about it in terms of physics, what's the most powerful thing you've done today?